So today, I'm going to present one of our research that we are doing, which is about evaluating syntactic structure as a mechanism for logical reasoning in language model. My name is Alex Anvi Eponon, and I'm currently doing my PhD degree in AI, natural language processing, in Mexico. So, about the problem and the motivations that actually pushed us to do this work. First of all, was the distributional approach. Modern AI has moved away from syntactic formalism in favor of a distributional semantic pattern recognition, and also the scaling problem, but also we have our hypothesis. The idea is that recent LLMs basically display, how can I say, some reasoning capabilities, but this is a surface level, and we basically want to somehow find better ways that use less data. So our research question is, can explicit syntactic decomposition enhance logical reasoning in language model without requiring large-scale pre-training or architectural scaling? And through our state-of-the-art research and the findings that we had, first, we saw that there are several paradigms, and one of the most important in this is the compositionality in language. What is it? It's just a principle that the meaning of complex expressions is derived from their parts and the rules governing their combinations. And the challenge with LLM is that they have some apparent good reasoning abilities, but as I was saying, it's just on the surface level patterns and like kind of recognition patterns, not a structural, well organized inside the representations. And the current state of the art models achieve reasoning through expensive scaling strategies, raising questions about whether increased complexity is truly necessary. And one of the key insights that we actually saw is the case of hypergraph. And hypergraph are kind of a bit similar, if we can say, uh, to graphs, basically, but in a different ways, where we try to model higher order correlations. And we saw that, empirically speaking, that this was reducing 80% of the data for training the models or to do fine tunings while keeping high the reasoning of the models. So in that experiment that we actually did, it was basically to use a syntactic aspect of language because we are dealing with LLMs. And in English, one of the things that basically we know a canonical rule is the subject verb object manner place time framework, basically to construct the sentence. But not only that, to evaluate questions, right? So the objective was using this modularity in syntax in English. Can we basically train and fine-tune the model to actually reason in this particular area with less data, with less model, and also observe this on, how can I say, on models that does not display, models that do not display reasoning. And we will see that in few minutes. So the goal, explicitly decompose linguistic inputs into interpretable structural components to evaluate whether syntactic decomposition enhances logical reasoning capabilities, especially in smaller models, right? So as an experiment setup, the models that we chose for now, we basically use one of the newest model like LFM DOS 2.5 thinking, which is a very recent model with 1.2 billion parameters. We also use a Quen 2.5 instruct, a Quen 1.5 chart, and until the Flan T5, which is the smallest model with 75 million parameters. And we can see that the first two models, LFM and Quen 2.5, both displays a reasoning capability. Both displays reasoning capabilities, and their training processes was including data. We're including data basically with reasoning. How can I say reasoning characteristics, right? And about the data set, we chose three data sets: the CWQ, multi-op other KJ, the hotspot, QA, and the drop. The characteristic with them is that they are basically questions. We call them multi-hop questions. That means that we need basically a different level of, how can I say, of reasoning before getting the answer back. And we took that because in order to answer the questions, you basically need to reason. So that's why we took basically those three data sets. And we could say here that the total of data sets samples that we chose is very small, 1,350 questions, because our assumption is that reasoning does not need too much data, right? So for that, that's why we actually shrank as small as possible the data in order to see if really the models will be able to reason correctly, right? So the setting, so basically throughout the experiment, we tried zero shot without the framework that I'm explaining, few shots, and after that, we actually continue with fine-tuned models. I mean, all of the models that we had. And we took into account the Rouge L, the sentence BERT, and the BERT score F1 as metrics, where basically the sentence BERT were actually the focus, and Rouge L too, because of the syntax overlap. So the first was the zero shot without basically the framework, and we saw that the new model that we actually the new model's LFM2 was the best. Basically answered the questions and through the zero shot because it's the newest model and it embeds basically the reasoning and thinking capabilities. And we also saw that much more closer was the Quen2 instruct. But this is first to see actually as a baseline how they behave in front of this kind of multi-hop complexity questions. And finally, when we would start the few shots with the few shots with only three examples, basically, we saw that the Quen 2.5 instruct was basically the best. And that's really interesting because we can all of them follow the same process about the few shots. We didn't change anything, but with only 500 million parameters, the model was able to actually beat the LFM2, the 2.5, which was the newest model about it. I mean, about reasoning capabilities and everything, right? And finally, when we continue a bit further with the fine tuning with our techniques, following exactly the same process without changing anything, we were able to see that the Quen 2.5, the small LM, which is much more older, and even the Quen 1.5 chart, were basically beating LFM 2.5 at reasoning capability, at reasoning on questions, the composition, basically to answer the questions. That was really interesting because small LM2 is only 135 million parameters, while LFM2 is basically 1.2 billion parameters. So these first empirical results were just demonstrating that syntactic structure combined with fine-tuning can dramatically close the gap between small and large language models at reasoning. Like, kind of, if we really do a very good job at the data side with making things high quality, we are able basically to embed, how can I say, reasoning into models. And regardless of the size of the models, I mean, the parameters. And here, actually, the Flan T5 and the Flying T5 small base and are actually under evaluation currently, right? That's why we don't display exactly the results. So the key findings, as we were able to see, is like the size is does not actually impact too much the reasoning proficiency of the model. We saw that a small LM2 and the Quen 2.5 were beating the LFM 2.5, which was basically one double size of LFM of the Quen 2.5 models, right? And also the other key insight was about the structure on porous small models. We saw that the small LM2 with fine-tuning achieves 88% at Rouge L, which is the syntactic overlap, and matching or exceeding models with 80% more parameters, right? We saw that. And explicit syntactic structure is computationally efficient alternative to scaling. This is mean that when we are able to basically embed, actually here it's not about memorizing, like giving the model a lot of samples for the data. No, it's basically create a specific type of data so that the model not actually try to memorize each sample that it sees during the training, but try to capture exactly the reasoning capability, the reasoning behind, like, let's say, the construction of these particular sentences or questions. So these questions, basically, this reasoning will be later, how can I say, generalized to other actually tasks, subtasks. So Basically, the feature works. What are the feature works? Targeted fine-tuning, further validation experiments to strengthen findings across additional models and datasets. When 1.5 instability, investigate the observed instability under the SVO MPT framework to understand interactions between architecture and static decompositions. Scientific domain application, develop strategies for extracting research questions in scientific domains where logical rigor and interpretability are critical. And finally, efficient and interpretable AI. Contribute to building AI systems grounding in compositional principle rather than brute force pattern matching. So basically, our objective through this research is at the level of the scientific domain. We really want to create systems not only to be really transparent and interpretable, but also at the same time to provide a systematic and automated way to discover new hypotheses, scientific hypotheses. That's why we actually use data sets that are actually about question decompositions and where basically the textual dataset was only question, right? So about the references, we had like different, as we could see here, a survey on compositional learning from Fresh ChatGPT and bridging compositional and distribution semantics, hypergraph, computation engineering, and compositional semantic parsing with large language models, high-order knowledge representation for agentic scientific reasoning, and finally, break it down, a question understanding benchmark. Thank you very much. If you